Hello, welcome to this Vib Tip session. Today we are going to talk about shock test and particularly about classical shocks. Within environmental testing, very often, together with vibration testing, we find shock tests. The most traditional type of shocks that has been defined in the standards are classical shocks. Classical shocks are defined by three parameters: the shape, the amplitude, and the duration. In terms of shape or waveform, we can find basically three types of shocks, which names are dictated by its shape. We can find half-sine shock, rectangular or trapezoidal, and initial or terminal peak sawtooth. In the real environment, these shapes are only similar to impact recordings on harder or softer surfaces, but all the other shocks don't look like classical shocks. Due to this fact, its use has been significantly reduced in the last years in favor of other more complex techniques, but classical shocks are still present in many standards, and it's interesting to study. We can use two different types of equipment to reproduce classical shocks. The shock machine includes a table where the DUT is fixed and is raised up by a crane. The height will determine the amplitude of the shock. Then it's left to drop down free, impacting on some elements called programmers. Depending on the type of programmers, we can get different shapes and duration. The equipment has a very heavy reaction mass to minimize force transmission to the surroundings. The signal we record is acceleration as a function of the time, and similar to the example in the image. For half-sine shocks, programmers are these of elastomeric materials with different rigidities and shapes. Depending on the stiffness and number of these, we get shorter or larger shock durations. For trapezoidal shock, the plunge impacts on a piston connected to a pressure chamber filled with gas nitrogen. The piston moves down quickly up to a point where it remains for a while, and then the rebound starts, generating the trapezoidal waveform. In this case, depending on the gas nitrogen precharge, the pulse will be high amplitude and short duration, or lower amplitude but longer duration. The type of results we get with a shock machine are normally not too precise. The waveform is not clean, and typically with significant ripple, and the repetitiveness is questionable. However, there are high-level pulses that can only be generated by the use of a shock machine. Shocks can be performed in vertical or in horizontal axes, as we see in the below video for battery testing. Whenever we can, we try to reproduce classical shock using shakers. With shakers, we get a more precise and accurate acceleration waveform. Two consecutive shocks are practically equal, and we can generate repetitive shocks at a defined rate. All these features are extremely difficult to reach with a shock machine. However, when we use a shaker for classical shock, there are two conditions that must be met. The shaker armature must start and end with zero velocity and must return to the initial position if we don't want the armature to get out of the shaker body. In the image, we can see that these two conditions force us to introduce two small amplitude pulses before and after the main pulse. These pulses are called pre-pulse and post-pulse, and most of the standards limit them to less than 20% of the pulse amplitude. When we perform classical shock with a vibration system, we need to check not only if we have enough force to reach the acceleration amplitude of the pulse, but the associated velocity and displacement. In terms of force, the manufacturers offer maximum shock force 2 times the maximum sine force, and it's necessary to ask for confirmation if our force requirement is higher. In terms of velocity and displacement, let's see with an example how the parameters of the pulse can affect them. Let's consider a half-sine pulse with rectangular pre- and post-pulse. We start with an amplitude of 50 Gs 6 millisecond duration and a typically 10% pre- and post-pulse. The shape of the resultant pulse is as we expected, and the values of both velocity close to 1 meters per second and displacement 11 millimeters peak to peak are well within usual shaker limits. Now let's extend the duration to 11 milliseconds. Both velocity and displacement increase significantly, but still within normal shaker performance. If now we increase the amplitude to 100 Gs, velocity raises up to a high 3.5 meters per second, and displacement moves up near the limit of 3 inches, 76 millimeters. If we increase the pre- and post-pulse up to a 15%, velocity is not affected, but displacement significantly decreases close to 2 inches. Last but not least, another advantage of performing classical shock with shaker is the capability of repetitive shocks with a rate of typically few seconds between pulses. This is inconceivable in a shock machine, where it takes many seconds to connect the crane, raise the platform up and let it drop free for its shocks. Summarizing, classical shocks have been commonly requested to certify the resistance of a product to shocks in its transportation or operational environment, although in most cases the real shock is different from the limited waveforms that we reproduce. Performing classical shock with shakers is more precise and clean than with shock machines, where we find tighter limits due to force, velocity, and displacement limitations. Want to learn more? Invest in education and sign up for our training courses. Thanks for attending, and let's meet in the next Vib Tip session.